So our first speaker is Imogen, Isabella Morris, and she'll talk about untangling Celtic knots. Or is it Celtic knots?
So you probably all have some idea of what a Celtic knot looks like, but just in case you want to try yourself, I've got some pictures. These ones were in the Lake District, and these ones were from around Edinburgh. That's in Morningside, and that's Max Hub. So you probably all also have an intuitive idea of what a knot is. It's where you get a piece of string and then you do some twiddly thing so that it makes a lump that won't come out. And a mathematical knot is really rather similar. It's just that you have to join the ends of the piece of string up, and then whatever you have in the string can't escape, and you can deform it how you sort of move it along how you like, and it's not going to change. So these are some knots I made earlier.
Lupita style.
You might be able to recognise this one as a Celtic knot, because it looks rather pretty and is a nice shape. But actually, all the previous knots were the same thing. So this raises a question: how do we tell when a knot is Celtic? Okay, so I'm just going to talk about Celtic plaits because they're easier, and they're a knot that you can draw on a grid, and you place a crossing at regular points on the grid, and they are alternating, which means that if you follow a strand of the knot, if it goes under at one crossing, then at the next crossing it must go over, and if it goes over at one crossing, then at the next crossing it must go under. So to give you some examples of the Celtic plaits, I'm going to show you a MATLAB program that I wrote for drawing them. Okay, so this, it says in the corner, this size of grid contains a knot. And the difference between a knot and a link is that a knot is just made from one circle with a twist in, and a link would have more than one. So let's look at one with a link in. Right, so the links are drawn in different colours so you can tell them apart. The arguments that you give the program specify the size of the grid, and the size of the grid is always going to be an even number. So if we call it an m by n grid, and because n and m are even, we divide by 2. But once you've done that, once you've got n over 2 and m over 2, then it's the highest common factor of them that gives the number of links in the knot. And you can see that that's true for this. Okay. This is a sort of general Celtic plaits drawn so that you can see the crossings, and we don't really specify what happens at the ends, but they're going to look like the corner here as well. Okay, so how can we recognise these Celtic plaits? Well, there's something called the Alexander polynomial, and this is a knot invariant. What that means is, if you have a given knot and you calculate its Alexander polynomial, the polynomial you get will be the same, even if you've calculated it for different projections of the knot. That means different ways of tangling it up, just as long as you've not actually undone the circle. But it's not perfect as a way of identifying the knots, because you could get two knots that are different but have the same Luxander polynomial, and that wouldn't tell you that they were the same, because there's different. But it's still something, and the way we calculate the Luxander polynomial is we first find the Cypher matrix, and then we get the polynomial from the determinant of that. Okay, so the Cypher matrix is found from the Cypher surface, and the Cypher surface is found using Cypher's algorithm. So Cypher's algorithm starts off by finding paths around the knot, and whenever it gets to a crossing, it decides to follow the strand that it wasn't following originally. And because you orientate the knot with a direction, and that shows you which path to take. Do an example. Okay. So,
can people at the back see the
No.
diagram? Maybe you can draw on the board on the left.
right. This is the simplest knot that isn't the unknot, i.e. isn't just a circle. So when we orientate it, we give it the stranded direction, an arrow, and then to find the Cypher circles, we follow it along till we get to a crossing, and then we won't take this strand because that's the strand we're going down. And now we have to decide, shall we go up that way or this way? Well, if we go down that way, then eventually the arrow would sort of conflict with, if we were just following the path of the strands, this arrow. So we won't choose that way either. We'll choose the way that wouldn't conflict if we just kept going down. And then we keep going along. And then we've gone down all of these strands, but we haven't reached this inner circle. So we do that separately, and then we find that that is also a nice circle. And to find the Cypher surface from this, we span, first we raise the circles so that they're not in the same plane, and then we span them with discs, which means you get a circle and then another circle above, but they're discs now. And there are crossings joining the circles. We keep those crossings joining the circles, but we make them into bands. So a band is like a ribbon. And because we used to have a crossing, and actually I forgot to mention this, but the Cypher surface is meant to be the surface bounded by the knot. So we want the strands of the knot to be like the edges of the surface. And so when the crossing, in this one there, it comes from, the strand comes that way and then it goes over the other strand, so we have to twist it like that. And so this is going to be an orientable surface, which means that the two sides of the surface will never meet if you choose to colour in one side green and the other side red. You're never going to get green and red mixing. And so there is this program called Cypherview where you can have a look at some of the Cypher surfaces.
I've also knitted a couple, which you can pass them around and have a look. So this is the trapdoor that she's drawn. There's a disc at the top and a disc at the bottom joined by the 3 bands. And there's another one you can pass the other way.
This is actually the separate surface of a Celtic plat, but not in its projection where you would recognise it as a plat. And you can also see what it would look like if you were walking along the surface. Okay, and we had this general sort of Celtic plat here before, and if we apply Cypher's algorithm to that, we get this Cypher surface. And the shaded side is a different side from the unshaded. So the Cypher matrix, the values in that matrix are the linking numbers of closed curves on the Cypher surface. The closed curves are curves that surround each hole in the Cypher surface. So if you just pick an arbitrary place on the Cypher surface to make a closed curve and you think, oh, I can make a closed curve here. If you try to make a closed curve here, then you can deform that into a point. But if you try to make a closed curve around here, then it can't go into the hole. So it's sort of stuck there. Here's the closed curves on the surface. And you can see that they go down bands together. And when they go down a band, two adjacent closed curves go down a band together, they get twisted together. And we can give a value to that twist, which is what gives us a linking number. And the linking number also depends on the orientation of the closed curve. So if that arrow was going that way and this arrow was going the other way, then it gives a different linking number than the one for where the closed curves are both having their arrows clockwise. So this is one of the possible scenarios. You can see that they're not really linked in this picture. You could just sort of pull them apart. Therefore, we give it a linking number of 0. This one, they are truly linked, but just once. They're just twisted around each other once. So we give it a linking number of 1 or -1, depending on the orientations of these curves. This one, they're linked around each other fully twice. So we give that a linking number of 2 or -2. Okay, so this is just the format that the Cypher matrix is going to take. We're going to put the linking numbers in the matrix in this form. And the main diagonal is closed curves that link with themselves. So if you had if you have a closed curve here, and then you put another one on, but you sort of raised it slightly off the surface, then it would twist with itself. And that gives a linking number. That would give this is the scenario in which that happens. And so, as you can see, the main diagonal of the matrix is going to be all 2's, because we saw from that diagram that the linking number is 2. And this diagonal is adjacent curves, and then this other kind of submatrix that makes up part of the matrix is also adjacent curves that are 1's. And the reason why we have a lot of 0's is that most curves aren't next to each other and don't link at all with each other. Okay, so how we calculate the Luxander polynomial from the Cypher matrix is matrix. So that's n minus the determinant of n minus 2 times n transpose. So we actually know the Alexander polynomial of the 7-4 knot, which is a kind of Celtic flat, and that one is 4t plus 4t inverse minus 7. And now let's see whether we get the same Alexander polynomial from the Cypher matrix that we had calculated for the Celtic knots. So the 7-4 knot is the knot drawn on the 4x6 grid. No.
Yep.
Okay. So that means that the size of the matrix we're going to get is 6, 4. So we have 6 divided by 2 is 3, and then minus 1, that's a 2, and then the other one is going to be a 1, so it's going to be 2 by 2. So one of this submatrix is going to be a 2 by 2 one, and this is just going to be a 1. So we get the first submatrix, first 2 by 2 version of this submatrix, which means just this one here. So when we do this of that, we get so it's 2 minus 2t minus t 1 and 2 minus 2t, and then the determinant of this is okay, and plus t, yes. That makes 4t squared plus 4 minus 7t. And so you notice that the t's aren't quite as I said they were, but you don't need to worry about it. And so this proves not that it's not that the 7-4 knot is a Celtic flat. It just shows that we haven't disproved it from being a Celtic flat. So it's not like there's still lots to be done, but at least we can discount a lot of knots from being Celtic flats when we find that the Alexander polynomial isn't right. Yeah. Thank you for listening. Are there any questions?
You tried to take one of the Celtic knots you showed at the beginning and tried to compute the Cypher matrix. Did that?
Oh, so one of the more complex ones.
Mm-hmm. Yeah. Oh, a real world one. Yeah. Or for example, that. How difficult would it be to? You don't have to do it. It's all right. It's just a question.
It wouldn't be too bad. There would be I think it would be best to like maybe untwist the bits that are quite obvious.
Irrelevant.
and
Nugatory.
You
Hate
get
called
a
it.
rather, you just get a rather complex surface that was hard to visualize and have to draw the close curves over that. But you could do it if you went through it rather systematically.
That's nice.
But the Cypher matrix wouldn't look as nice as the one in.
Yeah. Cypherview.
What makes those knots Celtic knots?
Okay, so I didn't properly define a Celtic knot. It's defined. The best definition I know is defined in terms of a grid, and you place crossings on the grid. I'll do a really small one. It has to be an even grid, and then you place a crossing on every point where the parity of, if this is the x-axis and that's the y-axis, then the parity of the x and y coordinates don't match. So if x is odd and y is even, or y is odd and x is even. So that's like there and there. And anyway, that would just give you a Celtic flat if you just place the crossings in any of those places. To get these ones, you'd have to put barriers, and that would stop you from putting crossings in certain places. And of course, you have to make the crossings alternating. And once you've placed all your crossings, then you join them up to basically the nearest crossing, and it just sort of comes out.
Any more questions?
Are there other families of knots other than Celtic that are similarly?
Yes, and in fact actually Celtic knots are more general than you think, because every alternating knot, every knot that has just one alternating projection will be a Celtic knot. But there are knots that don't have any alternating projection. And I'm not really sure how common they are, but I think they're more complex. I think you have to go quite large until you get to the first one. You have to have quite a large minimum crossing number before you get the first normal.
Okay, well, thank you very much.
Thank you.